understood that building a useful quantum computer was going to be a staggeringly hard engineering problem, if it was even possible at all.
For years, quantum computers were treated like fragile science fair trophies, impressive to look at, impossible to trust. Then Google built Willow, and something changed. This machine didn't just run fast, it stayed awake, running for 10 straight hours, repeating the same quantum experiment until reality itself started to look inefficient. Was it still a test or an interrogation? What happens when classical physics can't keep up anymore? And is speed really the breakthrough? Or is endurance the part that should worry us? So, what exactly did Willow do that made scientists quietly stop calling this a demo? The 5-minute run that broke time. It started with a task so simple on paper that it shattered time itself. What Willow was asked to do did not look dramatic. No secret code, no hidden message, no sci-fi problem pulled from a movie script. The task was called random circuit sampling, and in plain language, it means this. You feed a quantum computer a messy, highly random set of instructions and ask it to spit out the result. Not the most useful answer, not a correct answer you can check with a calculator. Just an answer that proves the machine actually followed the quantum rules instead of faking it. That sounds boring, right? But here is where it gets strange. For a classical computer, even the fastest supercomputer on Earth, simulating this exact task accurately would take an estimated 10 septillion years. That is 10 to the power of 25. How do you even comprehend a number like that? If you started when the universe was born and ran the simulation non-stop, you would still not be remotely close to finishing. Willow did it in under 5 minutes. Let that sit for a second. Not 5 hours, not 5 days, 5 minutes. The kind of time it takes to make coffee or scroll through a few posts. If a machine finishes before you blink, does time still matter in the way we think it does? At first, headlines rushed to call this a speed record, because that is the easiest story to tell. Faster machines make sense to us. We have lived through faster phones, faster internet, faster everything. But the scientists inside Google quietly stopped using the word faster, because faster was not the point anymore. This was not a race. This was a scale mismatch so extreme that the old language stopped working. The better word they started using was intractable. Intractable means not slow, not difficult, but fundamentally out of reach. It means no amount of optimization, no clever shortcut, and no future upgrade to classical machines would realistically close the gap. The problem was not that classical computers were bad at the task. It was that the task itself lives in a space that classical reality struggles to represent. And this is where things get uncomfortable. Random circuit sampling does not give you an answer you can verify step by step. You cannot check the math afterward. Instead, scientists verify it statistically by checking whether the output matches patterns that only a real quantum system could produce. In other words, Willow was not just computing, it was behaving. So, what exactly was happening inside that chip during those 5 minutes? Was it simply crunching numbers faster than anything we have ever built? Or was it exploring combinations that classical machines cannot even describe without collapsing under their own memory limits? At what point does computation stop feeling like calculation and start feeling like something else entirely? This is why the number 10 septillion years matters so much. It is not a flex. It is a warning label. It tells you that even if you gathered every atom in the observable universe and turned it into a classical computer, you would still be nowhere near matching what Willow did casually, almost indifferently. And remember, this was not a one-time stunt. Willow did not perform this task once and bowed out of it. It ran again, and again over hours. Each run reinforces the same uncomfortable conclusion. The gap was not closing, it was widening. This is the part mainstream coverage tends to skip because it is harder to explain and harder to sit with. When scientists say a problem is intractable, They are quietly admitting that our best models of reality have limits, not because we lack intelligence or funding, but because the universe itself might be doing something that classical logic cannot efficiently track. So when people ask whether this was just a benchmark or just a demo, the answer becomes slippery. Benchmarks are supposed to measure performance. This one exposed a boundary. It showed a place where our usual tools stop scaling. And Willow keeps going. Is this computation, or is it a glimpse of a different rulebook altogether? But speed alone means nothing if the machine falls apart after a few minutes. So why didn't Willow? Why quantum computers were never supposed to last this long? Because quantum machines usually collapse under their own noise. This is the part most headlines rush past, but it matters more than speed ever did. Quantum computers were never designed to run for long stretches of time. In fact, for decades, the assumption was the opposite.
I think this moment, it feels to us like the pioneers on the 1940s and 50s that were building the first digital computers.
You run a quantum circuit quickly, grab the result, and shut everything down before the system falls apart. That fragility is not a design flaw. It is baked into how quantum physics works. A qubit is not like a normal computer bit that calmly sits as a 0 or a 1. A qubit lives in a delicate balance, holding multiple possibilities at once. The problem is that this balance hates the real world. Heat, vibrations, stray electromagnetic signals, and even tiny imperfections in the hardware all interfere. Imagine trying to balance a spinning coin on a table while someone keeps tapping the surface. That loss of balance is called decoherence, and it is the main reason quantum computers usually fail fast. Here is the counterintuitive part. Adding more qubits does not make this easier. It makes it worse. Every new qubit adds more ways for the system to lose its quantum state. That is why early quantum machines could barely stay coherent for fractions of a second. So when people hear that Willow ran for hours, the natural reaction is disbelief. Why does adding more qubits usually make things worse instead of better? For nearly 30 years, this problem stalled the field. Scientists knew about quantum error correction in theory, but making it work in practice felt like chasing a mirage. The idea sounds simple. You spread information across multiple qubits so that if one misbehaves, the others can correct it. But quantum errors are not neat. They do not politely announce themselves. They leak in quietly, stacking up until the system gives up entirely. This is what researchers call the error threshold problem. If your error rate stays above a certain level, no amount of correction helps. You can add layers and layers of protection and still lose the signal. For decades, no one could prove that a real machine could cross that threshold in a sustained way. Can noise ever be beaten? Or can it only be managed long enough to grab a quick result? That is why Willow lasting matters more than Willow being fast. Instead of collapsing after seconds or minutes, the system stayed coherent long enough to repeatedly correct itself. Errors still happened, but they did not spiral out of control. They stayed contained. That may sound subtle, but in quantum computing, subtle is everything. It suggests that the machine was not fighting noise anymore. It was coexisting with it. Think about that for a moment. What would stable quantum time even look like? Not a perfect system with zero errors, because that does not exist, but a system where errors stop being fatal, where time stops being the enemy and becomes something you can work with. This is where the story shifts from impressive to unsettling. A quantum computer that only works briefly is a novelty. A quantum computer that works long enough to correct itself starts to feel like infrastructure. It stops being a fragile experiment and starts behaving like a platform. And platforms change everything. Because once you are no longer racing against collapse, you can ask harder questions. You can run deeper circuits. You can repeat experiments without resetting the universe each time. You can let patterns emerge instead of snatching snapshots before the system dies. This is why researchers were so careful with their wording. They were not celebrating perfection. They were acknowledging endurance. And endurance is the one thing quantum machines were never supposed to have. And this is where Willow quietly crossed a line no one expected, didn't it? The moment errors started shrinking instead of growing, Google scaled up and the errors went down. That sentence alone should sound wrong if you understand how quantum computing is supposed to behave. For decades, the rule was simple and unforgiving. More qubits meant more problems. More connections meant more noise.
That's one of the ones that requires probably like 1 million qubits or more to do, but we're working up.
Scale was the enemy. And yet, with Willow, the opposite started happening. The team didn't jump straight to something massive. They scaled carefully, building surface code grids step by step. First, a small 3x3 layout, then 5x5, then 7x7. Each grid was not about raw power, but about how qubits watched each other. Every qubit was no longer alone, silently failing in isolation. It became part of a neighborhood that could spot when something went wrong. And here is where researchers had to pause and double-check their own data. Every time the grid got bigger, the error rate did not climb. It dropped. In fact, it was roughly cut in half with each step. That is not optimization. That is a phase change. What happens when complexity becomes your shield instead of your enemy? Adding more moving parts actually makes the machine calmer instead of more chaotic. This was the moment error correction stopped being theoretical and started behaving like a law of nature. To understand why this matters, you have to understand what below threshold really means. For years, quantum theory predicted a tipping point. If your physical error rate fell below a certain threshold, error correction would finally work faster than errors could accumulate. Above it, everything collapses. Below it, stability emerges. The problem was that no real machine could prove it in practice. Until now. With Willow, researchers crossed that threshold. Errors still existed, but they shrank faster than they spread. Instead of growing exponentially, they decayed. That is the difference between fighting a wildfire and watching a spark burn itself out. And once that happens, time changes. Suddenly, you are not limited to one clean run before decoherence wins. You can repeat circuits. You can extend them. You can let the system evolve long enough to reveal patterns instead of noise. This is how Willow managed to run experiments not just for minutes, but for hours. 10 hours quietly correcting itself in the background. Think about how strange that is. A machine operating in a domain where time used to be toxic suddenly becomes comfortable staying there. What would stable quantum time even look like if this keeps scaling? This is also why it took 3 decades to achieve. Not because scientists were lazy or underfunded, but because the margin for success was microscopic. Every layer had to improve together. Hardware quality, control electronics, calibration, algorithms. One weak link and the whole system slips back above the threshold and collapses. So when people frame this as just another incremental breakthrough, they miss the point. This was not about hitting a bigger number. It was about flipping the direction of failure itself. Errors no longer snowballed. They faded. Did we just cross the point of no return for quantum computing? That is the uncomfortable question experts are now quietly asking each other. Because once errors shrink with scale, the road ahead changes completely. Bigger machines stop looking impossible and start looking inevitable. And inevitability has consequences. Stability unlocked something far stranger than speed. The experiment that had to be repeated, and repeated, and repeated. They didn't run Willow once. They ran it relentlessly. Stability opened the door, but repetition kicked it wide open. Once Willow could stay coherent long enough to trust its own memory, researchers stopped asking simple questions and started asking dangerous ones. Not questions about speed, but about reversibility, about chaos, about whether a quantum system can be scrambled, and then politely asked to retrace its steps. This is where quantum echoes enter the story. The idea is deceptively simple. You take a quantum system and scramble it, mixing information so thoroughly that it looks lost. Then you make a tiny change, something almost invisible, and try to reverse the entire process. If the system really remembers its past, that tiny change will leave a measurable scar. That scar is the echo. What does it mean to reverse chaos, even briefly? In classical systems, chaos spreads fast and never comes back. Once information is lost, it stays lost. But quantum systems play by different rules, and those rules are what Willow was built to test. Here is the catch. You cannot run this experiment once and trust it. The signal you are looking for is faint, buried under noise. So you repeat it, over and over. You scramble, perturb, reverse, and measure, again and again and again. Each repetition sharpens the picture, like stacking exposures in low-light photography. This is why the experiment took hours. Not because Willow was slow, but because the question demanded patience. Repetition is not glamorous, but it is merciless. Why is repetition more terrifying than raw speed? Because it turns flukes into facts. As the data accumulated, something else became clear. Verifying these quantum echoes is not just hard for classical computers. It is borderline impossible at scale. To check whether the echo is real, you need to simulate parts of the same chaotic evolution. That simulation explodes in complexity almost immediately. Classical systems drown in memory requirements long before they get close. So researchers had to rely on internal consistency, patterns across runs, statistical signatures that only make sense if the quantum process is doing what it claims. If reality leaves fingerprints, who gets to read them when no classical mirror exists? This is where Willow quietly crossed from demonstration into advantage. Not a flashy one-time win, but a sustained edge. It could perform an experiment, repeat it enough times to build confidence, and do so in a regime where classical verification lags behind. That gap is subtle, but it matters more than headlines suggest. Think about the implications. A machine that can explore chaotic quantum behavior repeatedly, reliably, and faster than classical systems can verify. That is not just computation. That is experimentation at a new scale. And it only works because the machine does not fall apart halfway through. Each hour Willow kept running was proof that error correction was doing its job. Each repetition added weight to the result. This is why the team emphasized endurance. A single run could be luck. Hundreds of runs tell a story. And the story started to look strange. As echoes formed and decayed, the data began to show patterns that were not supposed to be easy. Patterns that hinted at how information spreads and hides in quantum systems. Patterns that raised uncomfortable questions about predictability itself. Is chaos truly random? Or does it follow rules we just cannot compute classically? And if a quantum machine can read those rules, what does that say about the limits of our current models? This is the moment where excitement turned into quiet focus inside the lab. Not panic, not a celebration, concentration, because something unsettling showed up in the data. What they actually found, and why it made scientists nervous. Not perfection, something more dangerous. After hours of clean runs and reassuring statistics, Willow started revealing a pattern that short demos are physically incapable of showing.
Willow is Google's newest and most powerful superconducting quantum computing chip.
Roughly once every hour, something unusual would happen. Not a total failure, not a dramatic collapse, but a rare correlated error. Multiple qubits are drifting together in a way that error correction was not designed to expect. On average, the system looked healthy. That is the trap. Average success hides rare events, and rare events are what break complex systems. Why do rare failures matter more than average success? Because they are the ones that scale with time. In a 5-minute demo, you never see them. In a 10-hour run, you cannot avoid them. These correlated errors did not come from a single faulty qubit or a bad calibration pulse. They emerged from interactions, from the system acting as a whole, because it means the enemy of quantum scaling is not just noise, but structure. The more coherent the system becomes, the more it can fail in ways that look organized. This is the paradox Willow exposed. Stability lets you run longer. Running longer lets you see deeper. Seeing deeper reveals failure modes that were invisible before. And once you see them, you cannot unsee them. What happens when machines outpace our ability to debug them? That question used to belong to science fiction. Now it sits quietly inside research papers. Engineers could point to error rates dropping overall, but those rare hourly events refused to vanish. They whispered that something new was happening in the system. This is why endurance changes the rules of discovery. When machines only run briefly, we design theories around snapshots. When they run for hours, the timeline itself becomes part of the experiment. You stop asking whether the system works and start asking how it fails over time. And the answer was uncomfortable. These correlated errors hinted that certain quantum states, once reached, make the system vulnerable. Not broken, just exposed. Like a bridge that holds thousands of cars until a very specific vibration sets in. The structure is sound, but the pattern is dangerous. Are we ready for systems we don't fully understand, even when they are technically doing what we asked? This is why researchers did not frame Willow's results as a clean victory. They framed them as a map showing where quantum computing is strong and where it might crack under pressure. And that map only exists because the machine kept running long enough to draw it. In a strange way, this was the real breakthrough. Not speed, not even stability, visibility. Because once you can observe rare failure modes, you can design around them. But that also means admitting they exist. And admitting they exist means admitting that quantum systems are crossing into regimes where intuition stops being reliable. That is the nerve Willow touched. It showed that quantum machines are no longer fragile toys. They are complex, evolving systems with emergent behavior. Systems that behave well most of the time and, strangely, some of the time. Systems that reward patience and punish assumptions. And then came the realization that this machine wasn't just computing anymore. The real unsettling discovery: quantum as a data factory. Willow didn't find answers. It found a new role. Up to this point, it is tempting to frame everything as a computing story. Faster calculations, longer runs, better error correction. But somewhere between hour 3 and hour 10, a quieter realization settled in. Willow was not just solving problems. It was producing something no classical machine can manufacture at scale. Data. Not synthetic data, not simulated guesses, but measurements pulled directly from quantum behavior itself. Each run, each echo, and each rare failure event became a record of how reality behaves when pushed into regimes that classical systems cannot follow. And once you see it that way, the breakthrough looks very different.
I've been fascinated with quantum computing since I first experimented with qubits in 2008. And since coming to Google in 2015,
quantum computers are often described as engines for answers. Willow hinted at something more disruptive: a quantum computer as a data factory. Think about what Willow was generating during those long runs. Vast amounts of high-fidelity measurements from chaotic quantum systems. Measurements that classical machines cannot reliably predict, reproduce, or even fully verify. That means these datasets are not just large. They are exclusive. Who owns reality's most accurate measurements when only a few machines on Earth can produce them? This is where the implications start to stretch beyond physics labs. Because data is not just evidence, it is fuel, especially for artificial intelligence. Modern AI systems thrive on patterns, correlations, and edge cases, and Willow was producing exactly that. Rare events, long-tail behaviors, subtle correlations that only emerge over time. What happens when AI trains on data that classical machines cannot generate? When models learn from quantum fingerprints instead of approximations? The advantage would not come from smarter algorithms, but from better access to reality itself. And it does not stop at AI. In life sciences, chemistry, and materials research. Understanding how complex systems evolve at a microscopic level is everything. Quantum simulations are already used to approximate molecules and reactions. But approximations have limits. A machine like Willow can observe those systems directly, again and again, long enough to reveal behaviors that short runs miss. This is the shift nobody advertised. Power moving from computation to measurement. For decades, science has been limited by what we can calculate. Now the bottleneck may become what we can observe and store. And that leads to a new concept quietly emerging in the background: the quantum audit log. Every long run Willow performed left a trace, a chronological record of quantum behavior under controlled conditions. Not a single answer, but a history. Over time, those histories become reference points, baselines, receipts. If a future machine claims a result, you can compare it to the log. Does it behave the same way? Do the rare errors line up? Do the echoes decay at the same rate? This is how trust gets built in systems we cannot fully simulate. But trust cuts both ways. Once a few organizations control the most detailed measurements of quantum reality, they also control the standards, the benchmarks, the definitions of what counts as correct. Is this the start of a new scientific hierarchy where access matters more than insight? Notice how different this feels from the usual hype. This is not about breaking encryption tomorrow or simulating the universe next week. It is about quietly becoming the best observer in the room, the one with the cleanest instruments and the longest memory. And that is unsettling in a very human way, because measurement shapes belief. The more accurate your measurements, the more confidently you can say what is real. When classical tools fall behind, their explanations start to look like stories instead of facts. This is why endurance mattered so much. 10 hours was not about bragging rights. It was about letting the system reveal itself honestly. No cherry-picked runs, no hiding rare behavior, just letting the machine speak long enough to hear what it repeats. And what it repeated was consistency mixed with surprise, order mixed with rare instability, patterns that only show up when you stop rushing. So, when people ask whether Willow found something unsettling, the honest answer is yes. Not because it uncovered a scary secret, but because it reframed what quantum machines are for. Not just calculators, but witnesses. And that brings us to the question everyone keeps asking. Maybe the wrong way? Did it prove the multiverse? Or something worse? No, and yes. And that's the problem. Every time a quantum breakthrough makes headlines, the multiverse sneaks back into the conversation. The idea is tempting. If a quantum computer explores many possibilities at once, maybe those possibilities live in parallel worlds. Some physicists, most famously David Deutsch, have argued that this is the clearest explanation. Quantum computation works so well, in this view, because reality itself is doing the parallel processing. But Google has been careful, almost cautious to a fault. No claims of other universes, no dramatic statements about proof, just data, measurements, and controlled language. And yet, the discomfort refuses to go away. Here's why. When Willow performs tasks that would take classical machines longer than the age of the universe to simulate, it forces an awkward question. If computation demands parallelism, where does it come from? Is it hiding in unseen branches of reality? Or is our classical picture simply too thin to capture what is really happening? Many physicists lean toward the second option. They argue that quantum mechanics does not require extra universes, just mathematics that behaves in unfamiliar ways. Classical reality, in this view, is an approximation layer, a simplified interface that works well enough most of the time until it doesn't. And Willow pushed straight into the until it doesn't zone. This is why Google avoids philosophical victory laps. Once you say multiverse, you stop doing science and start doing metaphysics. The experiments do not force that conclusion, but they also do not let you dismiss it comfortably. That tension sits right at the heart of the unsettling feeling people report when they read about Willow. Is nature hiding a structure we can't simulate classically, even in principle? Or are we just bad at describing what we are already using? Think about the quantum echoes again. The system scrambles information, reverses it, and reveals traces that only make sense if information is both spread out and recoverable in ways classical intuition fails to predict. That does not scream many worlds, but it does whisper that reality is doing more bookkeeping than we can track. And then there's endurance. Running for 10 hours straight matters philosophically, not just technically. Short experiments can be dismissed as tricks. Long ones start to feel like behavior. When a system keeps producing consistent results across hours of chaotic evolution, it challenges the idea that quantum weirdness is just a fragile illusion. Are we observing reality or negotiating with it through increasingly precise instruments? This is where the something worse part comes in. Not worse as in dangerous, but worse as in harder to ignore. Willow suggests that classical reality may not be the foundation we thought it was, but a convenient summary, a compression, useful, familiar, and incomplete. That idea is far more unsettling than a multiverse headline. Parallel worlds are exotic but distant. A reality that only works because we refuse to look too closely is much closer to home. And this is why the debate will not die down. Willow did not prove the multiverse, but it did prove that our explanations are under pressure. The more capable our machines become, the more they expose the gaps in how we explain what they are doing. So what does 10 hours straight really mean? Willow didn't uncover a cosmic secret. It uncovered a limit to how long classical reality can keep explaining itself before the cracks show. The unsettling truth isn't that quantum computers are fast. It's that they're patient. They don't rush to answers. They sit with uncertainty until patterns surface. So when a machine can question reality for hours without blinking, what happens when it never stops? Do you see quantum computers as tools or tests? What unsettles you more, speed or endurance? Like the video, subscribe, and stay curious.